Good afternoon. Welcome to this colloquium. I'm very pleased to introduce to you Professor Kate Scholberg. She's visiting us from Duke University, where she is a distinguished professor. She is a very active experimental physicist, active in neutrino physics, particle physics, nuclear physics. So Kate got her bachelor degree at McGill University in Canada. And after that, she got her master and PhD at Caltech. After that, she got fellowships at Boston University, and she was at MIT for 4 years, I believe. And then after that, she moved to Duke, where she has been since 2004. She is a member of many large neutrino experiments. She's currently the spokesperson of an experiment called Coherent that we will hear about in her colloquium. And then she is also very active on other experiments like Super Kamiokande, all neutrino experiments, Super Kamiokande, T2K, and Dune, which is kind of the next frontier in neutrino physics. So we will hear about neutrino physics and what's going on with Coherent and related physics. Okay, so thank you, Kate, for coming.
Thank you very much for that introduction. And it's a pleasure to be here. So what I'm going to tell you about is the Coherent experiment. Mostly, I'm going to tell you about scattering in Neutrino Alley. And so here's a rough outline of what I'm going to tell you about. I'm first going to tell you generally about neutrinos and neutrino interactions, just to set the scene. I'm going to tell you about the particular interaction that we're interested in here for this experiment, and go through motivations for why we're interested, tell you how we measure it, and then tell you about the results, the first light result about 5 years ago, and then the ongoing results coming in, and then finally prospects for the future. So neutrinos, let me start with the big picture. So in the standard model, we have these three families of fundamental fermions. We have these three families of quarks, and then we have the leptons that include the familiar electron and then heavier sibling, the muon and the tau. And in the standard model of particle physics, the neutral leptons are the neutrinos, and they're partners to the charged leptons up here. And they come in these three families. We don't actually really understand the reason for this pattern. The neutrinos have zero charge. They're neutral. They don't interact electromagnetically. They're fermions. They have spin a half. And in the standard model, they interact only via the weak interaction. We know that they interact also via gravity, but that's a whole other story that I'm not going to talk about. We know that they do have a tiny mass, but that is not what the subject of this colloquium is. Why do we care about them? Why do they matter? Well, they are part of the big picture. They are fundamental particles, and we want to understand the fundamental particles and their interactions in general. So we want to understand the properties of neutrinos for that reason. They matter in astrophysical systems. In fact, I guess I'm going to give a seminar tomorrow about neutrinos in supernovae. They are basically emitted in large numbers by different kinds of astrophysical objects, and studying them can tell us about those about astrophysics. And furthermore, the properties of astrophysical objects are important for understanding the properties of neutrinos. Same kind of thing for nuclear physics. We can learn about nuclei using neutrinos, and furthermore, the understanding of nuclear physics helps us understand neutrinos. And then for cosmology, neutrinos are part of the big size scale picture. They are constituents of the universe. They probably make up, well, we know they make up some of the dark matter, not all of the dark matter, but they are important for example, galaxy formation, for basically understanding the history of the universe. And neutrinos are emitted over enormous scales of energy. So this is the axis here going from less than EV of energy up to EEV. And the way I remember the sequence, this is, my God, that's pretty energetic. So you have, basically neutrinos that are wild neutrinos that are coming from natural sources up here above this line here. So starting from relic neutrinos from the Big Bang, neutrinos that are emitted by the sun and supernovae, neutrinos that come from cosmic ray showers in the atmosphere, and then finally neutrinos that are very high energy neutrinos emitted by exotic astrophysical objects, so spanning an enormous range of energies. Over still a large range of energies, not quite as wide as the natural ones, we have tame neutrinos, basically neutrinos that are produced by humans artificially. And these include neutrinos from artificial radioactive sources, from nuclear reactors, and from accelerators. And in fact, it's neutrinos from accelerators that I'm mostly going to talk about here. Neutrinos interact rarely. They interact only via the weak interaction, but they do sometimes interact. They are aloof, but not completely unsociable. And there are really two categories of neutrino interactions in the standard model. There are new charge current interactions that occur via the exchange of a virtual W charged W boson with a quark or a lepton. And this has the hallmark that the lepton has the same flavor as the incoming neutrino. And because, of course, mass energy must be conserved, the neutrino has to have enough oomph to create the rest mass in the final state. And so this typically has a threshold where you have to have enough energy to make that lepton in the final state. What I'm actually going to be talking about here is a neutral current interaction, which is a flavor blind interaction. Doesn't care about the flavor of the neutrino at all, or to a very large extent. And this is an interaction that goes by exchange of a neutral Z boson. And if it's just a scattering, then it doesn't have a threshold that occurs at any neutrino energy. And neutrinos interact with nuclei, entire nuclei, actually over this range of energies here. And at the very highest energies, so GeV, hundreds of GeV and beyond, you have neutrinos that are interacting with quarks inside a nucleus. And in fact, you can think of it as a, in terms of the de Broglie wavelength of the neutrino, at high energy, you have a very small de Broglie wavelength, and the neutrino is interacting with the smallest constituents of a nucleus, so basically with quarks. And these tend to be quite violent interactions. What will happen is the energy of the neutrino will get spread into the whole nucleus and basically blow it up into smithereens. This is what's called a deep inelastic scattering kind of interaction. And that's actually not what I'm going to be mostly talking about here. Oops, backwards. If you go down a little bit in energy, in the GeV range, this is actually where it's important for oscillation experiments, actually. This is where you have interactions with the neutrino with the nucleon, so with protons and neutrons inside a nucleus. So the de Broglie wavelength is a little bit bigger, and the interaction scale will be the scale of a nucleon. These can also be fairly disruptive. You can actually spray out junk from the nucleus. You can get energy that is converted into rest mass of mesons, other kinds of stuff. You can make hadrons. So this is a much messier kind of thing. Actually, this is an interesting and complicated regime to study for other reasons. Going down a little bit more, this is also an interesting regime in the, say, tens to MeV regime. This is where supernova neutrinos live. You have interactions with nuclei that tend to be minimally disruptive of a nucleus. They might change a nucleus into another kind of nucleus, and you might get some debris getting spit off, but it's not so disruptive. I'm actually not going to talk about this either. What I'm actually going to talk about is the very lowest energy regime here, where the de Broglie wavelength of the neutrino is relatively large, of the scale of the nucleus, and the neutrino just basically gently smacks a nucleus and the nucleus goes rolling off. And this is what's called coherent elastic neutrino nucleus scattering. So it's really the least disruptive and gentle energy regime for neutrino nucleus interactions. So this is the interaction. Sevens, coherent elastic neutrino nucleus scattering, where you have a neutrino that interacts with the nucleus, with an entire nucleus by exchange of a D boson, and basically the nucleus recoils as an intact entity, as a nucleus. It's kind of like smacking that apple and it goes rolling off. Being a little bit more quantitative about this, you can think of this as having the nucleon wave functions of the target in phase with each other from the point of view of the scattering. And this kind of coherent interaction, this is a hallmark of coherence, the total cross-section, the total interaction rate will scale as the single constituent cross-section times the square of the number of constituents. So that's kind of a general hallmark of a coherent kind of interaction. And this occurs, this is the condition, Q is the momentum transfer, R is the size of the nucleus. If this product is small, then the interaction will be coherent. And this occurs if you plug in the numbers for a medium-sized nucleus. For neutrino energies up to about 50 MeV, the interactions will be to a large extent coherent. A large fraction of them will result in just a nucleus rolling off rather than any kind of disruption of the nucleus or any kind of interaction with the internal structure of the nucleus. Okay, so here's an aside just on nomenclature. In the older literature for regarding this process, there were a lot of different acronyms, CNS, CNNS, ENNS. I much prefer including E for elastic, because otherwise this can be confused with a higher energy interaction, which may leave a nucleus intact, but may also create some other particle in the final state, such as a pion. This is a GeV scale kind of process. Actually, also interesting itself, but this is not what I'm talking about. There's nothing new created in the final state. I was taken to task by nuclear physicists for using NN, because to them that means nucleon, nucleon. You can use a little Greek letter here, and I'm actually kind of okay with that, but it's always annoying to constantly have to change the font. And so my preference here is sevens, where the neutrino is written as a V. And this is easy to say, it's pronounced as sevens. And actually, I think I've been fairly successful so far in spreading this meme. This is actually fairly commonly used now. The existence of this process was actually proposed decades ago in the 1970s in this paper here by Dan Friedman, where he called the suggestion of the existence of sevens, although it wasn't called sevens in those days, he called it an act of hubris because of the grave experimental difficulties in actually observing the process. Now here's and I'll come to the difficulties in a bit. So here's now in the standard model, this is the differential cross-section for this process, meaning basically that tells you the rate of scattering into, it gives you the distribution of recoil energies when the process occurs, and also the absolute rate with which that happens. And so here's the expression in the standard model. So this parameter here, this is GF, this is the Fermi constant. This is a standard model parameter that gives the essential strength of the weak interaction. This quantity over here is kinematics, and this is really actually a very simple thing. It's basically like a ping pong ball hitting a bowling ball. You know, it's basically just billiard ball kind of kinematics here. This quantity here is the form factor. So this is the Fourier transform of the nucleon spatial distribution, which describes the non-point likeness of a nucleus. If this form factor is 1, then the nucleus just looks like a single structureless object. It looks like a point to the neutrino. And so this is in fact the regime where we're pretty close to that. It's not perfectly true. The nucleus is not exactly a point. Q is the momentum transfer here. And then this quantity here is the weak nuclear charge. This is also in the standard model here, and it's given by this expression here, where Z is the number of protons in the nucleus, and it's the number of neutrons. This sine squared theta W is a parameter of nature. That's also a standard model parameter. It's the weak mixing angle or Weinberg angle here. And it turns out that the sine squared theta W happens to be about 1/4. That's just what the value of it happens to be. 4 times 1/4 is approximately 1. 1 minus 1 is approximately 0, or 1 minus approximately 1 is approximately 0. And so this prefactor here in front of the number of protons is a very small quantity. And so what that's saying is that the weak nuclear charge is really dominated by the number of neutrons you have. It really only cares about the neutrons. It doesn't care very much about the protons at all. And that means that in this expression, so QW is approximately equal to N, and so the differential cross-section is going to be proportional to the square of the number of neutrons in the nucleus to a good degree. And so that's just expressing that here. And what this plot shows is the cross-section as a function of neutron number in the nucleus. This is averaged over a particular flux, which I'm going to come back to what that flux is. But what you can see here, the feature of this plot, this is cross-section versus neutron number. This thin black line is just if you have a form factor of 1, so if it's really exactly a point. If it is not exactly a point, which a nucleus isn't, then you do get a suppression here. That's with a particular assumption. And the width of that green line is the uncertainty in that assumption. So it's actually quite well understood how much the nucleus isn't a point. And so this is basically the n squared dependence. And here I've plotted particular instances of isotopes, which are not chosen randomly, as you'll see. And so this kind of relation between the cross-section and the neutron number is a hallmark of this coherent process. This is a standard model prediction of what we expect. And the nuclear uncertainties on it are very small because the nucleus is just a very simple looking object in this kind of energy regime. And by neutrino standards, this cross-section is actually very big. Now, neutrinos are famously weakly interacting. And this interaction is weak, but it is not as weak as some of the standard kinds of neutrino interactions that our neutrino physicists are used to working with. And so this is an example here. This is a plot here showing the cross-section now as a function of neutrino energy going up to about 50 MeV. And this is interaction on electrons, which is a very small cross section. It's a log scale spanning lots of orders of magnitude. This red one is what's called inverse data decay. That's electron antineutrinos on protons. And actually, this is a kind of famously large interaction strength used for a lot of neutrino experiments. This green one is interaction on iodine, a regular charge current interaction on iodine. And what these other lines show here are interactions of sevens on different nuclei. And so if you compare for iodine up here, this dotted line, it's 2 orders of magnitude larger than the regular charge current cross-section, which is an interaction on a nucleon inside the nucleus. And so this is the n-squared enhancement. It's approximately 2-order enhancement of the interaction. You get 2 orders of magnitude, approximately more interactions by sevens than with a regular neutrino interaction. Okay, so it's a large cross-section by neutrino standards. And so you might say, what's the deal with Dan Friedman? What's with all the grave experimental difficulties? It should be happening all the time. Why is it so hard? And so this is the reason. The reason is basically kinematics. It's like hitting the bowling ball with a ping pong ball. That's not too hard to do, but it's hard to get that bowling ball moving very fast. And so this is an example of the kinematics. So this is basically this term here so this is an example for a medium-sized nucleus germanium for a monochromatic 30 MeV neutrino. And this is the recoil spectrum. So this is what this expression gives you. It's the distribution of recoil energies that you get from interacting that 30 MeV neutrino with a germanium nucleus. And the maximum here, which occurs when this term is 0, it goes as 2e squared over m. This maximum, and m is big, of course, this maximum is only 25 keV. And that is a tiny energy for a neutrino detector to detect. So super K, for example, famous neutrino detector, enormous neutrino detector, its threshold is a few MeV. So it would never see anything of this low energy, okay? Or even big scintillator, it's just, this is a tiny, whispery, tiny amount of energy that is very hard to observe. And so that's what the grave experimental difficulties are, is that you get the interaction happening a lot, but you get hardly any recoils. And the only way you can see it is to somehow couple that energy, that little tiny bit of energy, into something that is graspable and digitizable, and turn it into something you can measure. You have to somehow figure out how to couple that bit of energy into a signal. And what we've actually benefited a lot from in the past several decades is the development of detectors designed to do exactly this, to gather that little tiny bump, the result of that little tiny bump of energy, and turn it into something you can see. And what has actually done this is the community that has really made enormous progress is the community developing detectors for looking for direct dark matter detection. And that's exactly, in fact, the signal of a WIMP comes in, bumps a nucleus, and there's a little bit of energy that you can grasp and then turn into something that you can see. And now there's actually quite a range of different detector technologies that are sensitive in the range of a few to a few tenths of keV nuclear recoils. Okay, so that was what sevens is. Now, what's it good for? Why do we care? Why do we want to measure this? And there are so many reasons. I could talk a lot about this, but I'm going to pick only a few of them. So they fall into these general categories. One is that it's a signal for signatures of new physics, perhaps beyond the standard model. Another is it's a signal for understanding, I say, old physics, but also very interesting physics, by which I mean nuclear physics. In fact, if you get precise enough, you can learn about the structure of nuclei. It's a background for signatures of new physics, in particular for dark matter experiments. So you want to understand it for that reason. This is one of my favorite ones, although I'm not going to say too much about it. It's a signal for astrophysics as well. You can use it to see supernova neutrinos or solar neutrinos, for example. And then finally, I'm not going to say too much, but because the cross-section is so much larger, it's in principle possible to use sevens as a tool for reactor monitoring or monitoring for other kinds of things, spent nuclear fuel and so on. So there's also possible, even very practical benefits. So I'm going to zoom in a little bit onto the motivation of sevens as a signature of new physics. And so this really hinges on what I've really already said, is that this form factor here is the only place where the structure of the nucleus goes in to this expression. And these uncertainties are actually quite small. They're at the several percent level currently. And just to say again, on this plot here, the nuclear uncertainties are represented by the width of that green line on that plot. So it's not a very large uncertainty, it's few percent. And what this means is that if you see something different, so it means that the standard model prediction is very crisp, it's very precise. And if you see something that is different from that, that could be pointing to some new physics. Now, of course, if you get precise enough, if you get down to the few percent level, then you could be actually probing nuclear physics. But that's somewhere where we're not there yet. And here's just one example. There's many, many examples of this, just to give you one concept of the kind of thing you look for in the signature. You can have a non-standard interaction of a neutrino that is specific to neutrinos. So you can have some kind of new interaction, some sort of new mediator that isn't part of the standard model. And this is a way to parameterize it. There are these traditional, they're called epsilon. So this is basically you add a term to Lagrangian that describes the new interaction. These epsilons, if they're order of unity, that means there's some new interaction that has about the strength of a standard model, weak interaction. Currently, some of these are not very well disconstrained. If they are not zero, you would expect the sevens event rate to be either larger or smaller. If the mediator is heavy, you get a basically either a suppression or an enhancement. And so this is just an example of a parameter space. If you have a new interaction of electron neutrinos and d quarks, or a new interaction of electron neutrinos and u quarks, you can accidentally get the standard model rate if the parameters are conspire to do that. But if you have an excess, that could point to the parameters over here. If you have a suppression, that could point to parameters over there. And so the signature in this sort of scenario, which is a very simplified one, but the signature is that if you see more or less than you expect, then that could be some kind of new physics. And so that is an approach for looking for something new. Let me say a little bit about this one. Sevens is a background for signatures of new physics, and in particular dark matter physics. And sevens from natural neutrinos. So there's a whole class of experiments. I think people here are involved in some of them, where the idea is to look for relic WIMPs that make up the dark matter of the universe, or part of the dark matter of the universe. And the way you can tell that we are in some sea of WIMPs is that occasionally they will bump into nuclei and leave a little trace of energy deposition. And the thing is that the WIMPs will leave a little trace, a bumped nucleus that looks exactly like what a neutrino would do. Now, neutrinos are everywhere. They're coming from the sun. They're coming from the atmosphere all over the place. And so if your detectors are sensitive enough to see WIMPs, if they're very sensitive to see WIMPs in a certain parameter range, they will actually be blinded by neutrinos from natural sources. And so this is a standard plot that is shown a lot in dark matter direct detection physics, where this axis here is the dark matter mass. And this axis is the coupling of the dark matter. And this is the kind of plot that you want to place a point, a truth point on. If you're a dark matter physicist, I was told today that this is a propaganda plot, but I don't know if I wouldn't describe it that way. But the idea is that if you're a dark matter direct detection experiment and you don't see anything, you rule out swaths of this kind of parameter space of dark matter mass and coupling. And the thing is that if your detectors, and so this is kind of the current state of the art here, if your detectors are sensitive enough, then the more sensitive they are, the more they can move down. And if you have a detector that is sensitive to these parameters here, in fact, it's so sensitive that it will be blinded by sevens coming from neutrinos from the sun. And this concept here, that there's this range of parameters below which, if your detectors are sensitive to those dark matter parameters, they will actually be dominated by recoils from natural neutrinos. This is called the neutrino floor. These days, it's actually called the neutrino fog sometimes, since it's actually somewhat mushily known. I actually prefer to call it the neutrino glare, because it's also a signal potential signal. But that is basically the idea. We want to understand the sevens in order to understand, maximize the reach of our direct detection experiment. If you don't understand this, then you will do worse on your direct dark matter. And so this is just where these neutrinos are coming from that dominate the floor here. There's neutrinos from the sun over here. These are neutrinos from supernova, historical supernova, and atmospheric neutrinos up here. I can also mention this briefly. You can also look for dark matter that is produced by accelerators. There are classes of models where that will create dark matter that will create a nuclear recoil signature in your experiment. And sevens will be also the background for this kind of artificially produced dark matter as well. So it's sort of the same concept. You can't really tell event by event, whether a little bump is a neutrino or a dark matter particle, either whether it's relic neutrinos or whether it's a relic dark matter or whether it's accelerator produced. And so you want to understand your sevens for that reason. I'll say a little bit about this. Sevens is a signal for astrophysics. And here it's basically that neutrinos that come from any source at low energy, if they're in the regime where sevens dominates, they will create seven signals in detectors. So neutrinos coming from core collapse supernovae are what you get when a star reaches at the end of its life and it collapses into a neutron star or a black hole. What you get is neutrinos and antineutrinos of all flavors in a very sharp burst over a few tens of seconds. And these neutrinos have tens of MeV energies. And this is this kind of burst was observed once in 1987, and we're awaiting the next one. And this burst of neutrinos would be, in fact, observed in dark matter detectors worldwide. These detectors that are built to look for WIMPs in a steady state would also see a flash within 10 seconds of many sevens events coming from the flux of neutrinos that come from a supernova burst. And so this is just an example here. This is the events over a threshold. This is recoil energy threshold up to 50 keV. This is for different materials that are popularly used for underground low background dark matter detection. And you get a handful of events per ton of material, and these detectors are now reaching multi-ton scale, and that is sensitive to the entire flux. That's in contrast to most supernova neutrino detectors, which are sensitive only to part of the flux, part of the flavor components. And here's just an example. These are dark matter detectors that are made of xenon, where the next generation is a 40-ton scale. And this is the kind of signal you would see. You'd see hundreds of events all within 10 seconds or so in a detector like Darwin, this next generation detector. And this would be a tremendously valuable segment of the signal that you would get from a supernova neutrino, because it's sensitive to all the flavors. And furthermore, solar neutrinos make sevens. And in fact, the detectors, this is one of those propaganda plots here. This is results from a xenon detector. And this is where you expect the neutrino floor to be, and it's sort of not quite grazing it. Really, it's limits on the sevens from the sun. And eventually, however, these detectors are going to hit that floor. And in fact, there are nice things to see on the floor sometimes when you look down. And just to dramatize this region here is the diffuse supernova neutrino flux. And the supernova burst flux is about 9 or 10 orders of magnitude greater than that, greater than the leftover neutrinos from supernova. And so in about 10 seconds, you get enormous, it's like the floor is coming up to smack you in the face. It's really, you would get this really bright burst. Okay, now how to measure this? So as I mentioned before, I showed this before, the only signature is this little teeny bit of energy. You need a source. If you want to do this in the laboratory and not wait for a supernova or get a detector that's big and sensitive enough to see it from the sun, then ideally you want to make artificial neutrinos and use those to see sevens. And so what do you want in this source? You want a lot of neutrinos. That's always true. You want a high flux. You want a well understood spectrum. That's actually quite important if you're trying to, for example, tell the difference between the standard model rate and what you observe. You have to know what the flux is to high precision as well. You want to have, if possible, multiple flavors, because new physics may manifest itself as a flavor-dependent phenomenon. So it might be different. There might be something special about sevens. There might be new interactions from muon neutrinos, but not electron neutrinos, for example. And so ideally, if you're searching for the unknown, you want to have multiple flavors. This turns out to be really super important. You want a source that is pulsed, because these kind of experiments are all about the background. And if you know when your neutrinos are coming in pulses, then you can remove the background extremely effectively. And furthermore, know what your background is, so you only care about the square root of the background and not the background itself. You want to get close. This is really just related to the flux. And of course, you want practical access and so on. Now, the world community has been engaged, actually since the time of Dan Friedman's suggestion, has been engaged in looking for sevens from reactor neutrinos. In fact, this kind of thing is still ongoing. And this is not at all a dumb idea, because reactors produce enormous quantities of neutrinos. So nuclear reactors produce in fission reactions. They actually produce electron antineutrinos primarily, with energies up to about 8 MeV or so. And the fluxes are enormous. It's something like 10 to the 20 per gigawatt, or 2 times 10 to the 20 per gigawatt. So it's really lots and lots of neutrinos. And sometimes you can get very close to a reactor as well. So that's great. But the problem here, the reason this is really hard, is that the energies of the neutrinos are low enough that you get very, very low recoil energies. And that becomes a huge challenge on the detector side. And so here's just kind of another illustration of this. So this left-hand plot is the maximum recoil energy as a function of neutrino energy. And so this is what I showed you before. It goes as E squared over M. This is for argon, so a medium to small nucleus. And so that red line is this maximum recoil energy. And so you can see if you're at where reactor neutrinos are, if you've got like say 5 MeV or 3 MeV, your recoil energy is less than 1 keV. Okay, so that is really, really hard to detect. That's very challenging. But if you're at 30 MeV or so, you can see that your recoils are greater than 10 keV, and that is totally within the regime of current dark matter detector capabilities. Here's another plot. This also illustrates that the cross-section also scales with the square of the neutrino energy. And so you want to have a little more neutrino energy, you actually get more interactions with more neutrino energy. And so this is another illustration actually showing both the cross-section and the recoil energy effect. This is for 30 MeV neutrinos. This is for monochromatic neutrinos for the same flux. So you imagine it's the same flux. This is for 30 MeV neutrinos. This is for 3 MeV neutrinos. So the 3 MeV neutrinos you see, and they max out much less than 1 keV. 30 MeV neutrinos max out at much higher energies. And furthermore, you get 2 orders of magnitude more of them, more interactions. So you might say, okay, why not just keep dialing up the neutrino energy? Isn't that better? Isn't more energy better? And the answer is you can't go too crazy, because if your energy is too high, then you start to scatter preferentially off the nucleons, and the interactions become preferentially incoherent. You end up with inelastic interactions on nucleons and no longer have a high degree of coherence. And so you actually want their momentum transfer to be small. And quantitatively, this means you want your energies to be less than about 50 MeV if you want to have a good fraction of coherent interactions. And so that kind of tells you where the sweet spot is, which is a few tens of MeV. And it turns out we are very lucky that it is possible to make a source of neutrinos of a few tens of MeV, and that is neutrinos that come from pion decay at rest. And so this is a source of neutrinos that actually you get if you take protons and you smash them into a material that makes pions. So you make lots of mesons like pions. The pions, the negative ones get captured, they get sucked up by nuclei. The positive ones will then decay at rest. And so the pion decay here is predominantly a 2-body decay. And this gives you, because it's 2-body, it gives you a monochromatic 30 MeV neutrino of muon flavor. Okay, and so this is a very sharp line. If it's really decaying at rest, you get a sharp monochromatic neutrino. That's what this red line is here at 30 MeV. Then if the muon subsequently decays at rest, that's a 3-body decay. The nature of this decay is well understood. It comes from weak physics, and you get a well understood energy spectrum of electron neutrinos here that go up to half the mass of the muon, up to 50 MeV. And then muon antineutrinos, which also go up to 50 MeV. And that shape of that spectrum is extremely well understood. Okay. And so this is really, and it gives you energies of a few tens of MeV, which is great for having a high level of coherence and also a high event rate. Now, this sort of source of neutrinos has actually been used for some decades by different experiments and around the world. And so here's just a map showing some of the blue ones that are sources that have been used in the past. The green ones are current, and the red ones are future. And so there's lots of history. If you want to do a figure of merit, if you want to compare how good these experiments are in making pion decay at rest neutrinos, stop pion neutrinos, this is the plot here where the x-axis here, this is a figure of merit plot. This x-axis here is the total neutrino flux, which is approximately proportional to the power in protons of the source. This is a background rejection factor. And so this actually turns out to be really important, that the more tightly pulsed the proton beam is, the better you can reject the background. And so this is related to the inverse of the duty cycle here. And so a high value here means a very tightly pulsed beam. And these diagonal lines are ISO signal over square root of background, figure of merit kind of thing. And so these are the sources that I showed you before. And you can see that these ones are in the upper right corner, where you have the best, it's the most pulsed and combination of pulsing and total number of neutrinos. And so what I'm going to talk about here is the spallation neutron source, which is the source that we've been using for coherent. Okay, so the SNS, the spallation neutron source, it's at Oak Ridge in Tennessee. It was actually built for nothing to do with neutrinos. It was built to make neutrons for all kinds of science. It's a $1 billion facility. It's built for doing engineering and biology and all sorts of other things. Neutrons are condensed matter physics used for all kinds of things. It has a proton beam energy of about a GeV. The power is about 1.4 megawatts currently. It's actually going to go up. And the pulsing is very tight. It's 400 nanosecond pulses at 60 hertz. So that's actually very widely spaced, bright pulses. This is the target that the protons hit. This is made of liquid mercury, and it's an enormous thing. It's terrifying. It's like a meter scale thing. And basically, it's so dense and large that almost every pion that is produced immediately comes to a screeching halt and decays at rest. You know, it's really a very high fraction of decay at rest. And the best thing is the neutrinos are free. It's basically completely parasitic. This was not designed in, but you really could not build or design a better neutrino source, which is just fantastic luck. And this is just to illustrate, this is not what I'm talking about. They're not free neutrinos like this. It's free neutrinos like this. It's just fabulous neutrinos. We were super lucky to find this facility. And so here's the time structure. This is a 60 hertz source. And what we get here is a 40 nanosecond proton pulse. This is where you get the muon neutrinos that are prompt in time with the pulse, because muon, the pions decay very fast. The muon decay timescale is 2.2 microsecond, and this is where you get the delayed component from the muon decay. And if this happens at 60 hertz, very widely spaced, you get a background rejection of a few times 10 to the minus 4. So it's really very, very favorable for background. This is from a detailed simulation of the flux. You know, basically putting in all the details. This is on a log scale, and this here is that stopped pion spectrum that I showed you. There is some extra garbage that isn't from pion decay at rest, for example, decay in flight, kaons, and so on. But this is really suppressed by orders of magnitude, so it's really super clean. It's 99% of decay at rest. It's a very, very clean source of neutrinos. Okay, so that's the source. I hope I've convinced you that the SNS is fantastic. Now, how do you detect the neutrinos? And as I mentioned, we now have really enormous number of tools for detecting exactly very low energy recoils, mostly in the context of WIMP detection. And there are many strategies. Just roughly, you can look for phonons, basically look for a temperature increase. That tends to be relatively slow, but that's something you can do. You can put a electric field on it and gather ionization and get a pulse, you know, basically feel a little zap there. You can also, if the energy gets coupled into photons, you can measure those photons and see a little flash. And there's several technologies. There's actually in WIMP world, in dark matter world, there's lots of strategies of combining the signals. We actually haven't done that yet, but it's something that we may do in the future. Okay, so here's the collaboration. This is a coherent collaboration. It's 90 people, 20 institutions, 4 countries. This is actually, by high energy physics standards, quite small collaboration. By other standards, a large one. We have 4 main detector technologies, actually more than I'm going to tell you about, that make use of different kinds of energy deposition coupling to digitization. So we have a scintillating crystal. This is the first measurement I'll tell you about. We have also argon scintillator. We have germanium, which is a ionization collection kind of device, and then sodium iodide, which is also a scintillator. They are masses of tens of kilogram scale. This one is much larger. I'll say a little tiny bit more about that. And they have recoil energy thresholds of around 10 keV or so, 10 or a few tens of keV. And we're able to deploy them on the order of 20 meters from the SNS source of neutrinos. And this is another thing where we really super lucked out. It turned out that there was a storage hallway that ran parallel to the beam only 20 meters away from where the source is. And so that was tremendous. This is what we call neutrino alley. So here's where the proton beam comes in. That's where that mercury target for the SNS that creates the neutron is located. This is this hallway. It's actually got about 8 meters of reduced water equivalent of overburden that actually shields out some cosmic rays, which is also really a nice bonus. And it turns out that all this region in here is filled in with concrete and rubble, which shields out all the neutrons, which is also just fantastic because neutrons are not our friends. The SNS is in fact is a neutron source. And so this is where we have occupied this hallway. That's a view looking down it. This is a view of the detectors that are installed along there. And we can just sit there and bask in this isotropic glow of neutrinos that come from the SNS that are going to come no matter what they do with the SNS. You know, the neutrinos are there. Our job is to stop as many of them as possible. And so here's a sanitized plot of the energy distribution of the recoils that we expect. This is for our detectors, and it's scaled by mass and scaled by distance, by the so inverse square of distance. And so here are the targets. We have different amounts of target. And here you can kind of see the kinematics in action. If you have a really heavy nucleus like cesium iodide, you actually get more events per mass, but you get them kicked to lower energy. If you have a light target, you get fewer events per detector mass, but you get them kicked to higher energy. And so this green line is for sodium. You get more high energy recoils. The red line is for cesium iodide. Backgrounds, it's actually in practice, this is what we spend all our time on. It sounds, all those plots were sanitized before, but in practice, backgrounds are what you have to deal with. You have the usual kind of things. You've got conflict rays, you've got ambient radioactivity, you've got radioactivity in your detector. Detectors also have whatever their particular quirks are. They have noises and dark rates and so on. However, the thing about these ones, these are steady state backgrounds. And if you have a beam pulse, you can almost completely remove those or you know, and characterize them perfectly. You only care about the square root of them. If you know what their rate is, you just subtract them. And if you know when your neutrinos are coming. And so these are not really so scary. The ones that are scarier are the neutrons that come from the spallation neutron source because they are correlated with the beam. And so this is in fact what we spend a lot of our time doing, is trying to characterize these neutrons that come along with the beam that actually depend on the location within the hallway. So we actually have to work pretty hard to characterize those, although it turns out they're quite tractable. And right in the middle of the alley, we actually have very few of them. Here's the first light detector. This was cesium iodide, and this is ran for about 4 years, maybe 3 years. So this is just showing the different layers of shielding, and we still do worry about backgrounds, even if it's not as much as as a WIMP detector would have to worry about for steady state signal. This is a really, by neutrino detector standards, a tiny detector. It's something you can hold in your hand. Consider Super K, which is 40 meters high. This is really a very small detector, 14.5 kilograms. Those are grad students, both of whom have now graduated. This is what it looks like in its shielding in Neutrino Alley. And this is the first light result, which came out in 2017 and was on the cover of Science. And this is the distribution. This is for this is photoelectrons, which is proportional to recoil energy deposition. So it's basically the light that you see in the scintillator. The brighter the light, the more the energy deposition. This is the this is the timing here, the arrival time. And so here, this is basically a projection in energy. So this is basically a measure of the recoil energy distribution, which tells you about the momentum transfer. And the points here, background subtracted, the green histograms are the prediction from the standard model, showing the different flavor content. And you can see that it really matches very well. So we're basically seeing the standard model rate in the cesium iodide. So this was the first measurement with about half the total data sample. And on this plot here, this is the n squared plot here. This is what we expect in the standard model. This was the first light result, is a little bit low, but within 1 sigma of the standard model prediction. So this is the first measurement. And even this measurement, this is a 30% measurement. Even this first measurement was enough to constrain new physics beyond the standard model. So this is an example. This is the same parameter space I showed you before. The gray blob here was the knowledge, the allowed region for those parameters from previous experiments. And what we were able to do is constrain those parameters under the assumption that all the others are 0 to be within this region. And so we're already, even with this very crude measurement, able to make some statements about new physics, constrain new physics beyond the standard model. Next measurement, this one came out in 2020, is the single phase liquid argon detector. So in the corner of Neutrino Alley, we have a 24 kilogram vessel of liquid argon viewed by 2 photomultiplier tubes. So liquid argon is also a scintillator and gives little flashes of light when you get recoils in it. That's what it looks like looking in. It's got wavelength shifter on the inside. That's a photomultiplier tube covered with wavelength shifter. This ran actually in a couple of different phases since 2017. And this one in that corner of Neutrino Alley, we actually have more neutrons, but it's still tractable. We have to spend a little more time trying to characterize them, but we are able to do that. And so this is the plot here of energy, deposited energy here. This is recoil energy here, and these are the data. This dashed line is our background. So we do have BRN means beam-related neutrons. We have neutrons there. This dotted line is the fitted signal, and there is a clear excess of signal over background. And so that is our second measurement. The first measurement was 6 sigma, actually 6.7 sigma. This one is about 3.2 sigma, so not quite as significant, but definitely there. This is our latest measurement result. This is with the full CZMI data set, twice the statistics, very clean, matches the expectation. In the CZMI, we're actually right in the middle of the alley. There's almost no neutrons. You can see this purple is the beam-related neutrons. It's a very small component. We have a very clean and good match of the signal to the expectation. And so this is where we are right now in measurements on the n-square plot. This is with the full CZMI data set. The error bars are squished down. We actually also had a campaign of a lot of improvement of understanding the detector response. And you can see it's still maybe a teeny bit on the low side, but really fully consistent with the standard model. For argon, we have a measurement also consistent with the standard model, maybe less than 1 sigma on the high side, but basically standard model. And so there, and that's in a much smaller value of n. Okay, so that's the status of the data, and these data even further constrain new physics. This is the same plot where there's a big filled in band before. Now we've got a smaller region. These are other combinations of parameters, and so really these measures, and this is just the tip of the iceberg for this kind of thing. There's actually quite a lot of different constraints you can make on physics beyond the standard model with this kind of measurement. And this is one more thing. This is another kind of thing we can do. We can actually look for accelerator produced dark matter. I mentioned this briefly. If you have dark matter coming from the SNS target, there's lots of exciting high energy stuff going on in there that can also produce in certain particular models, produce dark matter that would also make little recoils, but that this would look different from the neutrinos in that it would be harder, so basically higher energy, and also at shorter timescales. And so we can use our expected properties of dark matter to constrain there the neutrinos are the background. We can fit out possible contributions of the dark matter and actually put really quite stringent constraints on the parameters of this type of dark matter. In fact, in this particular case, we can actually get down to the cosmological expectation for scalar dark matter particles. So this is actually a new thing we're spending quite a bit of time exploring. Okay, so what's next? We've got 2 down, more to go. This is what we're planning and working on, in fact, deployment actively for several of these. So what we're planning is to add sodium iodide. And in fact, we have a lot of it. We have 3 tons of it. There's a whole bunch of sodium iodide detectors from an old Homeland Security program that we have stolen and borrowed and or were donated, and we are refurbishing them for use for sevens and actually other higher energy interactions, but that's another story. So we're deploying a lot of sodium iodide, and this is in the middle of deployment now. We have 1 module almost running and 4 more to go. We are deploying 18 kilograms of germanium, also under deployment right now. In fact, students were in the alley last week working on that, and we're aiming to be actually the next beam run is end of next month, and that's the aim for getting that up and running. We have funding now for ton scale argon, which will go in the same place and actually making use of some of the same infrastructure. And of course, that will enormously increase the statistics that we have from argon. And then there's also ideas for a higher light yield cryogenic cesium iodide crystal. And so this is just a table showing the status of these. So cesium iodide has been decommissioned. Germanium is now deployment in progress. Deployment of this is in progress, and then liquid argon, we are actually running kind of R&D right now in the location with we have funding for ton scale from Korea, in fact, and that will be deployed in 2024, or taking data, in fact, in 2024. And there's actually lots more stuff that I don't have time to talk about, but you can ask me about. And there's more to come. So this is a plot of the neutrino flux. So here's the this is the first target station. This is the SNS that where we're actually installed. We're actually right here. This is where the protons come in. These things are neutron beam lines, and Neutrino Alley is right here on that side. What is going to be built and running by the early 2030s, also not for neutrinos at all, for more neutrons, but we can benefit from the neutrinos, is a second target station. And the protons will be shared between this one and this one, between the first and the second target station. This plot here is an isoflux contour of the neutrinos that will emanate from both of these. Of course, we will know by the timing which target station the neutrino came from if we have a detector. And there are actually many exciting possibilities. This is going to double the total power. And really, there's lots of exciting possibilities for sighting, actually having a bit more space. Neutrino Alley is lovely, but it's a bit tight. We would like to have more space to deploy bigger detectors. And we actually have very interesting possibilities for doing that near the second target station, and also possibly in between for other particular physics, targeted physics searches. Let me just step back a little bit and put this in a bigger worldwide context. There are other SEVENS efforts worldwide. We're the only ones that have a result so far. But there are 2 other instances of SEVENS experiments at stopped pion sources. And then this actually isn't even complete, but there are many experiments that are trying to do this at reactors, where the challenge really is to get to very low thresholds. But there's actually a lot of really exciting novel technologies that I am convinced at some point in the next several years are going to succeed in making a measurement of SEVENS at a nuclear reactor, which will be very exciting. And here's a summary of SEVENS results overall. So the only measurement points are on this n² plot for stopped pion neutrinos. That's basically our 2 plots there from 2 points from coherent. Some of the dark matter experiments have put some limits on SEVENS from the sun. So there's xenon experiment that has not seen SEVENS from solar neutrinos, but can exclude abnormally large values. And so there's a limit here from the xenon experiment. There's actually, I think Panda X has one too. And then there are limits now from reactor experiments. This red line is the flux average cross section for reactors. And there are limits there. None of those experiments has yet succeeded, but I think prospects are quite good for actually having a successful detection sometime in the next 5 or 10 years, or maybe even sooner. All right, so I will summarize. Takeaway messages. SEVENS is this interaction that has a large cross section but tiny recoil, scales is n². It has become accessible now. The thing that made it possible to measure was that we were able to use low threshold detectors. We have these new detectors, and also this extra oomph and time structure of a stopped pion source is really what made it possible. We have this first measurement by coherent in 2 different materials now. And even that was enough to make meaningful bounds on beyond the standard model of physics. This is really still just the beginning. We have lots more going on, lots of ideas, actually lots of stuff I haven't even talked about. And there's other experiments that I'm sure will be very soon joining the fun. So I will stop there.